A very good morning to you all, and warm welcome to the day 2 of our short-term course on design of landfills and waste containment systems. So, as you're aware, sir, could you please give the option of multiple sharing, multi-participant sharing?
Yeah, you should have said co-host or something. Okay.
There was no, yeah.
Yeah. Okay, then you can turn it back to me. Okay, that's good.
Yeah.
Yeah.
Okay. So welcome back. There are 3 number of lectures scheduled today. So the first one will be delivered by Professor Krishna R. Reddy from University of Illinois, Chicago. The second lecture will be delivered by Dr. Ratnakar Mahajan, so who is an engineer at Mecca Ferry India Limited, and third will be delivered by myself, Dr. Hanumantha Rao from IIT Bhubaneswar. So I now request Dr. Remya to give a brief over the first presenter, Professor Krishna R. Reddy from University of Illinois at Chicago.
So good morning, everyone, and welcome to this first session of the second day of this short-term course. So we have with us Professor Krishna R. Reddy. We have already listened to him yesterday, and I know that we don't need any introduction. He's an expertise and very well-known person in his area of research. Just for the sake of formality, let me introduce Professor Reddy to the participants here. Professor Krishna R. Reddy is a university scholar, distinguished researcher, and professor in the Civil and Environmental Engineering, University of Chicago, Illinois, Chicago, US. He is also a director of Sustainable Engineering Research Laboratory and director of Geotechnical Engineering Laboratory in his university. So Professor Reddy received his PhD in civil engineering from Illinois Institute of Technology, US, and he received gold medal for being the first in BE civil engineering from Osmania University, Hyderabad, and ME civil engineering from and specialization in geotechnical engineering from IIT Roorkee. Prior to joining University of Illinois, Dr. Reddy worked as civil engineer and project manager for 3 years in industry, and also worked on several major civil and environmental engineering related projects. Dr. Reddy is a registered professional civil engineer and an envisioned sustainability professional. Dr. Reddy's teaching and research and as well as consultancy experience include geotechnical investigations and infrastructure, environmental pollution control and remediation technologies, waste management and beneficial reuse, as well as sustainable or resilient engineering. Dr. Reddy is an author of 4 major books, including the 2 which is widely used as a textbook. The first one is Geo-Environmental Engineering, Site Remediation, Waste Containment, and Emerging Waste Management Technologies. And the second is titled as Sustainable Engineering, Drivers, Metrics, Tools, and Applications. Dr. Reddy is also author of 2,000 journal papers of international repute. He has edited 21 books or conference proceedings. He has 22 book chapters to his credit and 226 full conference papers. He has an H index of 65 with a citation of more than 14,000. Dr. Reddy has given over 2,000 invited presentations in USA and 20 other countries. He has also received several awards of excellence in research and teaching, which include the ASCE Wesley Honor Award, ASTM Hogenschroeder Award, UIC Distinguished Researcher Award, University of Illinois Scholar Award, University of Illinois Award of Excellence in Teaching, etc. He's also a fellow of American Society of Civil Engineers, AST, diplomat of Geotechnical Engineering, and board certified environmental engineer. So with this brief introduction to his vast expertise, let me welcome Professor Reddy to take over this session and to deliver his lecture.
Yeah, thank you very much, Remya, for that nice introduction. So, can you hear me well?
Yes, sir.
Yes.
Okay. So now I'm going to share the presentation. Let's see here, this ratio. All right. Okay, can you see it? Right, it's good.
Yes, sir. Yes.
All right,
Yes,
so
sir, visible.
yeah, thank you so much for that introduction, Remya. So, so today's my talk is gas generation and management. Um, you this is my second talk in this short course. Before I get started, I want to thank Dr. Hanumantha Rao and also Remya for organizing this short course and inviting me to be a speaker. And I also want to thank you all for taking this short course. This is a great opportunity to learn the subject in so much in detail. So you are, really doing the right thing. So be proud of yourself for participating in this. I suggest everyone to mute your mic and switch off video so that, we will not have any, internet issues or, focus more on my presentation. So I suggest everyone to put your questions. Yeah, by the way, I want to post the presentation in the chat box at the end of my presentation. So don't get panicked about taking the screenshots of every slide that I'm going to show. So just like how I did it yesterday. So at the end of my presentation, I'm going to put the presentation in the chat box. You can download it, okay? But, please use it only for your personal use. Don't post it, in public domain because I have some figures in the presentation that are copyright protected. And type your questions in the chat box. At the end of my presentation, I will try to answer as many as I can. So let me start with this textbook or reference book. I recommend everyone working in the landfill area to have this book. And this book has 4 parts. And the third part in this book deals with landfills and impoundments. And in particular, in that part, these are different chapters: sources and characteristics of the waste, landfill regulations, siting configurations, liner systems, leachate collection and removal systems, and liner design, final cover systems, gas generation and management, groundwater monitoring, surface impoundments, beneficial use recycling, end use of closed landfills, bioreactor landfills. So these are all the topics that are in a logical sequence of how the landfill design has to be conducted. And I teach a graduate level class, it's a design of landfills and impoundments. I really follow these chapters in the same order that I'm showing here. So if you are interested in teaching a course, I recommend you to follow this. So in this, I'm lecturing about this one particular topic, gas generation and management. So if you want to get more details on my presentation later on, so you can refer to this chapter 20 in the book. So landfill gas generation. So that's the topic, today. So why would gas gets generated in a landfill, right? So that's the kind of a basic question. So the gas is generated because of the degradation of organic matter, organic components that you have in your waste. So if you don't have organics, generally, if you have inorganic waste, so you don't see any gases generating. But since you have organics in the municipal solid waste, you're going to generate the organics, generate the gas. And the gas is generated due to several mechanisms: evaporation and volatilization, chemical reactions, and biological decomposition. So out of these, all these three mechanisms, biological decomposition is the most dominant mechanism by which landfill gas is generated. One has to have an understanding of what organic components that you have in your municipal solid waste, because that is what is going to dictate how much gas you are going to generate, and at what rate you're going to generate. So you need to have a proper understanding of organic components in your municipal solid waste. So this kind of information, you could have it. For example, in the US, there's a lot of information from US EPA that shows the composition of the municipal solid waste. So as you see here, these are all the different components of municipal solid waste. And you can look at, what are the degradable components in here: paper, food, yard trimmings, wood to some extent, and plastics to some extent. So if you sum them up, then that's going to be your organic content that's has the potential to degrade. But as you see here, this is the municipal solid waste that is generated, before even recycling. So once it's generated, you do the recycling, you do composting, you take out some of the waste for different waste management purposes. But what we are concerned, in case of landfills, is what is the composition of the waste that is actually going to the landfill, that you're going to put it in a landfill. So that's the most important thing that you need to look at it. Okay, it's not about like the municipal solid waste that is generated, but it is the municipal solid waste that gets to the landfill. So the best way to know the composition of the municipal solid waste that is going to the landfill is to do the investigation. So you can collect a sample of waste that is coming to the landfill to get disposed of. That's kind of fresh waste. And if you want to know, how composition of the municipal solid waste at different locations, at different depths, you can drill it and then collect the samples at different locations, and then you try to look at what the composition is. So we did this kind of investigation in our past research projects. This is the project you can see in the picture. It was done 2006. It's many years ago. This was done at Orchard Hills Bioreactor Landfill. It's really close to Chicago. So we basically went to a landfill and then got the samples of the fresh waste that coming to the landfill, and then we drilled at different locations at different depths, and we collected the samples as you see in these pictures, right? So this is how you can really look at, and this waste has been, at some of these locations, waste has been there for some time. And then we wanted to know, what is the fresh waste composition is, what is the waste composition at different locations at different depths. So the collected waste, we wanted to know the composition of it. So what do we do, So for at each location, we get a lot of bags of samples, because you need to really have a large amount of, material to represent the municipal solid waste. It's not like a soil, right? So it's highly heterogeneous. So you get a lot of sample, and then you spread them on the tarp, and then you quarter it, you mix it, homogenize it, and you take the quarter of the sample. And then we do this, use the sieves, because we want to know the size distribution, not like a typical soil grain size distribution, but we have these three big size sieves. So we put them on the top, and then whatever is larger than that size retains on that one. Final one goes into the second one, and then third one. So there are three sieves. And then the idea is, we're going to look at what is retained on each sieve. We're going to look at, each component in it. And then we have 18 different categories of the components. So we have these boxes, set aside with the labels. And literally, we look at each piece. We look at each piece and then look at what it is. And then, depending upon, let's say it's plastic, it's glass, and then we put that in corresponding buckets. So this is me. You can see, we use the masks these days commonly for some other reason, but it's a stinky business. When you are working with the waste, you have to put mask. And this project, I did it when I had a postdoc, Céline Grillier from France, was working with me. So here, look at it. So we look at the first sieve, and then we take that one off, and then look at what is the second sieve, what is remaining on it. These are all the helpers. So, these are the landfill workers who are helping us out. And at the end, the finds that we have. So we look at that one and look at components that we have in that. So it's a very tedious, but we want to know the composition. So if you want to know composition, this is the only way that you can do it. So these are the three sieves. This is a large size. The openings are 100 millimeters, 50 millimeters, and 20 millimeters. And our waste components, these are the different waste categories, waste components that we designated. So as you see here, there are 18 different components, and there's a little bit description to what these different components are. So literally, we are looking at each piece in this in that sieve, and then putting in. We have this 18 small buckets on the side, so we are putting in those things. So after you do that one, you can do different calculations. You can do the distribution. You can look at the total quantities and all those things. But for degradation purposes, so you remember what I told you is the gas generation depends upon how much is your degradable fraction is. Not only that, you want to know how easily that organic material is degradable, how easily it can be degraded. So we categorize these components, into easily biodegradable waste, so like a cooking waste, garden waste, and then these components. You see these 4 different components. Those are moderately biodegradable waste, and hardly or difficult to biodegrade. These are these 3 components, and then we have a residual fines. The fine fraction, you cannot really distinguish different components in it. And then you have inert materials. So these are the ways that you could group your components and look at, the degradability of the waste, and then as a result, how much gas you're going to generate. So you can plot, this is the paper, that provides the description about how we did this. And then the results are also shown in that. So let's say fresh waste, how the results look for fresh waste. So this is the waste, that came to the landfill for fresh disposal, right? It came for disposal. So when you do this analysis, so you can look at it, how much is the, easily degradable fraction is only 6.9%. Moderately biodegradable fraction is 24.6%, and very difficult to degrade is 19.3%. Then you have inerts is 31%, and the residual fines, as I said, that could be degradable or maybe not. It's hard to know that one, but it's 18%. So you can see 31% is definitely inerts. This is all the other organic fraction that you're going to have in the waste. Now, in terms of the gas generation, you should know that this 6.9% is going to degrade very quickly, and that gas is going to come up. And then this moderately biodegradable fraction is going to start degrading. So that's going to take time. And then this difficult to biodegrade waste, that's going to take a longer time. So, even though you have these different organic fractions in the waste, it's going to take a long time for gas to generate. It's a slow process because of these different biodegradable characteristic components that you have in the waste. So that's how, we can kind of understand the, the gas evolution in a particular landfill. So just, I'm showing you the results of, this yellow is the fresh waste. And then these are all the, you see these bar charts that you see right next to the yellow. So those are all at different locations at different depths. So generally you have a lot of this difficult to biodegrade components in the landfill, and takes a long time for them to degrade and a long time for the gas to come out. So, but this easily biodegradable fraction, as you see, the initially how much you have, that's yellow, and the samples that we collected from the landfill, they were there for a couple of years. So you can see everything got biodegraded. And then eventually this moderately biodegradable fraction is going to degrade. This is the landfill that is undergoing degradation. So it will take a long time for these moderately and hardly biodegradable fractions to degrade. So a lot of times what happens is, if you conventionally, we look at loss on ignition, as organic matter. So basically you burn the waste at certain higher temperature, burn off the organics. So if you do that one, you get, whatever is the total percentage loss on ignition. But that is not going to give you a lot of detailed information. So as you see here, subdividing that one into easily biodegradable fraction, moderately biodegradable fraction, difficult to degrade fraction, plastics and fines, that gives you, even though you may have organics up to 60%, how much that can be easily degraded, how much is going to be difficult to degrade and takes time to degrade. So these kind of analysis can help you. So a lot of times, if you want to look at waste samples, from characteristics point of view, so you need to have this moisture content, and you need to have loss on ignition. The one thing that geotechs don't do that common is this biochemical methane potential. So it is very important to do this testing to determine what is the BMP, because that's the maximum methane potential, how much milliliters of methane that you can get per gram of waste. So that's very important characteristics if you want to understand, the extent of gas that came out or has potential to still, evolve. So, so those are the things, and you have percentage of fines, and then moisture content and temperature. Those are things that you look at it. So I'm showing here is the fresh waste. As you see, this is the moisture content, and the yellow is the loss on ignition, this organic content you see. And then BMP is this one that's showing here. So it's about 120 or 130 milliliter of methane per gram of waste. So that much potential it has. And then, when you have collected a waste sample from a landfill, you look at it and you compare with what is the fresh waste is. This is the moisture content. So there's a less moisture content compared to the fresh waste. And this yellow is the important thing. That's loss on ignition. You can see, it's reduced. And the most important thing is the BMP. You can see the BMP is very high. BMP is low. That means a lot of waste here at this location got degraded. And then you can look at temperature and other things. So you can do a lot of detailed analysis on the waste samples to understand the gas generation in the landfill. So as I mentioned, the mechanisms for gas generation is mostly the biological decomposition. And biological decomposition happens because you have a bacteria that is naturally present in the waste, that can degrade the contamination, degrade the waste, organic fraction, and how the waste degrades. Depending upon the literature, you will see there are 5 phases, 6 phases. Predominantly, there are 3 phases. Initially you have a aerobic decomposition, then your anaerobic decomposition, and the third is the methane production. So there's a lot of literature on the degradation of municipal solid waste. And then eventually, when you are in the phase 3, you're going to generate methane and carbon dioxide, almost equal amounts, and then you also could have trace amounts of other gaseous compounds. So you will see charts like this one. So initially the phase 1, where you have aerobic degradation, and then phase 2 and the phase 3. So I'm not going to spend too much time on this one. There's in the textbook in chapter 20, there's a more detailed description about these 3 different phases. So eventually, the first phase and the second phase are, they happen really fast, and third phase is going to continue for several years. And the third phase is the one where you have a methane and carbon dioxide and other non-methane organic compounds are going to be present in the gas. So the factors that affect the gas generation is the composition and the age of waste that I mentioned. If you have a fresh waste, you're going to get a lot of gas. But if it is in the landfill for a while, it's already produced some gas. So now, it may have a lower gas generation rate. So, the composition analysis that I mentioned, if you have already exhausted that easily degradable fraction and moderately degraded fraction, and then you have a difficult to degrade fraction, that's going to happen very slowly. And then, you're talking about the biodegradation. Those microbes should have, sufficient nutrients. And also, the microbes should have optimal temperature, and they should have optimum moisture content, and they should have optimum pH, and they should have optimal atmospheric conditions. So that's why this biodegradation and the gas evolution really varies from location to location in a landfill because of these varying environmental conditions. So it's very important to control these conditions to favor the degradation if you are hoping to get a good degradation. Okay, so one thing that we want to know in landfill gas, when you're dealing with landfill gases, is what is the gas composition and how much is the gas rate production that I'm going to get. So how much is the gas I'm going to produce, and what is the composition of it. So the best and the accurate way to know the specific gas composition is to install borehole probes or gas monitoring probes or gas extraction wells in a landfill. And then you basically collect the gas sample and analyze the gas, right? So that's the best scenario that you have it. So that's what a lot of people do that. One second. So my light was off. So that's the best way, right? So you just drill a hole and then collect the sample and then analyze it. And when you analyze it, you are going to basically analyze for methane, carbon dioxide, because those are the dominant byproducts of anaerobic degradation. And one thing that is becoming extremely important these days is non-methane organic compounds. So these have a huge potential for air pollution and could have a huge health impacts. And also the physical characteristics of the gas that you generate. So these are all the things that you can determine once you get your sample. So these chemical characteristics are the ones which are very important. And you cannot assume based on the literature. For example, if we see the gas composition in the U.S. landfills, you cannot assume the same composition in Indian landfills because the basic composition of the waste is different. These non-methane organic compounds, they really depend upon the waste composition. They are in a small quantities, but they could have a huge health impacts. So it's very important to look at, collect the gas samples and look at the composition in the location where you are. So this is the typical gas monitoring well. It's a standard practice. If you know site characterization, how you put a monitoring well or piezometer, it's kind of the same concept. You drill it and you put your filter pack and slotted pipe and filter pack, and then seal it off. And then you can collect the gas from there. And also you can, if you're interested in putting an in situ probe, you can put it in this one and isolate it, so that you are measuring the gas from certain location. And then, so that's how you get the gas composition. So the exact chemical composition, how much is the methane concentration, how much is the carbon dioxide concentration, and you could have H2S, other organic compounds, how much is the concentrations, you can find out that one. But the other thing that we want to know is also the gas production. How much gas I'm just producing, right? So that depends upon the type and extent and rate of decomposition, as I mentioned, the environmental conditions that I mentioned. So the best way to know how much is the gas production is, so you measure at the extraction wells. So you can put a flow meter and then measure it. So that would be the most exact way of doing it. And a lot of times, at the gas extraction wells, they do measure, what is the flow rate is. And based on the information from US landfills, it's 15,000 cubic yards per ton of waste with 54% methane, 46% CO2, and trace amounts of non-methane organic compounds. So that's kind of, don't take it as a universal number, but that's the typical, if you are looking at, hey, what could be the typical, range that you're looking at it. And then how much, that's the production that you could have, but how long it's going to take for that one to generate. It could be 20 years in humid areas, more than 100 years in very dry areas, and 8 to 15 years in bioreactor landfills where you adjust the moisture content and so forth, right? So this is kind of a general information, and that gives you an idea about the production. You can also use the methane production rate prediction mathematical models. So these are the different models that you can see, people have used in practice. So you can take a look at these models in my textbook. And also there is a US EPA land gem model that people use. It's an Excel-based simple model. And that is also can be used to predict the methane gas production. From there, you can infer what is the total landfill gas production is. So we looked at concentration and the landfill gas production. So we know that these things are going to happen, and they're not going to happen suddenly. It's going to take a longer time for them to, gas to evolve, and and the composition could change with time. So then the question is, why we need to worry about these landfill gases? Why do we need to worry, right? So we need to worry because methane is a major component of the landfill gas, and it's highly combustible. And there's a risk of explosion and fires as a result of the methane. So, you see landfills, it catches, on fire because of, this issue. And also, the methane is, odorless. You don't smell anything, but it's bad for, humans and animals from health point of view. And also, methane could be a good energy resource. And, if you are not using that one, you are wasting a good fuel resource. So these are the concerns with respect to the methane. And both methane and carbon dioxide are greenhouse gases, from climate change point of view. How important it is to control these gases. You don't want this one to be emitted into the atmosphere, right? And in the US, these landfills cause 1/3 of greenhouse emissions. So we cannot really ignore landfills, and we can do a lot of things to control this methane and carbon dioxide and control the greenhouse gases and help mitigate these global warming and climate impacts. The other common gas that is found in landfill, other gas that is found in landfill gas that is always a problematic is hydrogen sulfide. So this has bad odors, and oftentimes, neighbors from the landfill complain because of odor from hydrogen sulfide. So methane, you don't have any smell, any odor, so that does not create any issue. But hydrogen sulfide, could be in a small amount. Just say methane could be 50% or 52% or 48%. So hydrogen sulfide could be 1% or 2%, but it could create a lot of the problems in terms of the odors. And as I mentioned, these non-methane organic compounds are receiving a lot of attention these days, even though they are in trace amounts, but they are high, health risks to surrounding public. So you may know, people living surrounding the dump sites or landfills. Generally, they have very chronic, diseases, and many of them are attributed to these pollutants that is emitted from the landfills. The other problem is, if you don't deal with this landfill gas, what happens to landfill gas? It tries to come up towards the surface, and then even if you put a cover on it, so they're going to accumulate under the cover, and then they're going to build up the pressure, and with the pressure, the cover may blow out, or the cover might have vegetation. They could distress the roots, and then vegetation could be damaged. So these things are not acceptable. This is the classic picture that is shown, whenever you are dealing with the landfill gases, because this is the geomembrane that is in the final cover, and a lot of landfill gas got accumulated at the bottom, and then it's just there's no place to go. So it is just pressurizing the geomembrane and bulging it up into the air. So because of all these problems, we really need to do something about it. It's not only, we feel that it's good to do something about it, but regulations actually require us to do it. So yesterday's lecture, I mentioned that regulations are like, building codes, or these are the requirements the landfill operators and owners must do it. It's not optional. So RCRA in the US, we have Resource Conservation and Recovery Act, as I mentioned in my last lecture. And they have regulations on the methane concentration. So you cannot have 25% of the lower explosion limit in any facility structures. And at the facility boundary, at the landfill boundary, you cannot have more than LEL. So LEL is, for methane, is 5%. So you cannot have a more than 5% methane gas concentration at the boundary of your landfill. So because of that, you need to really monitor the methane concentrations throughout the landfill, and make sure that at the boundary, you're not exceeding this allowable limit. So if you exceed it, you are violating the law, and then you are punishable. So there's a strict punishment for that. So that requires you to monitor it and capture uh, the um, capture the gas. And Clean Air Act also kicks in because Clean Air Act does not permit all these air pollutants going into the atmosphere. So that's the big concern too. So because of that, you need to control these NMOCs. And then you could have additional state laws and regulations, and those needs to be considered too. So generally those are more stricter than these federal laws, as I mentioned, RCRA or Clean Air Act. So you have to do something. There's nothing like, oh, it's good to do something, I'm going to do something. No, if you have a landfill, you are required to do these things. So as a result, you need to think about capturing or controlling the gases. So as I mentioned, in my last lecture, yesterday's lecture, India has this solid waste rules of 2016, and the section F deals with ambient air quality monitoring at landfills. So they clearly tell you that landfill gas control systems, including the gas collection system, shall be installed at landfills to minimize the odor and all these problems that I mentioned. And also they have the same criteria like what we have in the US, 25% of the lower explosive limit. It should not be exceeded at landfill site. So it looks like anywhere at a landfill. And they'll tell you the option of how you can collect it, what you can do with that one, and then there is a ambient air quality monitoring requirements. So I think the requirements in Indian solid waste rules is similar to US rules. So my request for you is, okay, do you have any engineered landfills, municipal solid waste landfills in India following these rules? Visit one of them and try to know how they are designed, how they are being operated, and try to know the monitoring program. Now that you know about these landfill gases, so what kind of a monitoring that they are doing it, and how they are controlling the gases. And then, if you don't have an engineered landfill, visit a dump and highlight the problems and think of sustainable, practical solutions. So if you're thinking about, students assigning a research project for students or, project for students, these are the things that you could think about. So now that we have to do something, basically we need to collect the gases. And as I mentioned, you need to maintain the methane gas concentration 5% by volume at the landfill property line. But whereas Indian solid waste management rules, they say like entire landfill site. So to collect the gases, we have both the passive systems and active systems. So depending upon the situation, you could think about which one to use, or even combination of these passive and active gas collection systems you can use. So the passive gas collection systems could be these passive vertical wells. So just like a piezometers, if you know geotechnical characterization, to measure the measure the water levels, you put the piezometers, same thing like that. So you dig a well and then put a slotted pipe and put a filter pack around it, and then you seal it and you backfill with something. So this is in the landfill. So when the landfill gases come in here, so this is the final cover. So the landfill gases cannot go through the final cover. They enter into this high permeable filter pack, and then from there it comes up. So basically you are venting out into the air. And then you can also put this systems in cover system itself. So if you have a venting layer here, and then you can have pipes like this as shown here, and then you can vent those out. So basically you are taking out the gas from the landfill. And if you have a geomembrane in the final cover, you have to be very, very uh, you know, careful, because let's say, you have a barrier layer, soil layer, and you have a geomembrane, and then this pipe, the vent pipe has to come out, right? So the junction, where it is coming through that geomembrane, so that needs to be sealed properly. Otherwise, it's not going to do that infiltration function. That's the main purpose that you're putting it. You're trying to prevent the infiltration of precipitation. So here is the detail about it. This geosynthetics industry people, they know very well on how to, address this connection, so that you have a dual purpose. You're able to extract the gas, and then also prevent infiltration. So if you go to a landfill, the gas vents, they look like this. They pop up on the top of the landfill, or all over the landfill. You will see these gas vents like this. Or you could have a horizontal trenches. So you dig trenches in the waste, and then you have that gas collection pipe, and then from there you can vent it, and you also have an active gas collection system. So if you have a system, if you have a existing condition that does not allow gases to be collected in a passive manner, then you have to do the active gas collection. So basically here you apply the vacuum to suck up all the gas that is being produced in the waste. So a system typically could be like this. You have a series of extraction wells that you put in, and you connect them with the pipes, and then you apply the vacuum, and basically you're sucking up the gas from different locations, and then divert it to the gas treatment, or so this is the typical gas extraction well. So kind of a similar to pumping wells that we use in groundwater field. So slotted pipe, and then filter pack, and then you have a pipe, header pipe, and the gas is being extracted. So once you extract the gas, you literally, some places, you can vent it out, but a lot of places it's not allowed, based on the Clean Air Act. You cannot really, just vent it into the atmosphere. So you really have to treat it. So there are two ways to treat that gas. One is you just combust it and then release into the atmosphere. So you're not really recovering the energy out of this system, right? So a lot of times we use the flaring system for that one. Other one is you combust it with energy recovery. This is obviously the best option, because you don't want that energy to be wasted. So you may want to recover the landfill gas, methane, and then use it for energy recovery. But it depends, if energy recovery is financially practical or not. That's the question. But if that is not what you want to do, at least gas flaring is very commonly done at landfill. So basically, you are burning the landfill gas as it comes out, at 760 degrees centigrade to destroy all the gas constituents, and then the resultant products can be emitted into the atmosphere. So basically, you're controlling the air emissions. And then in this, you look at residence time, temperature, turbulence, oxygen, flame arrestor. So those are all the design factors, and you control them so that emissions are safe to put it into the atmosphere. So basically, you have a blower, that draws in gas from the landfill. It could be coming from, vertical wells, or trench system, or active, extraction system. And then that's diverted into the flare that I've shown here. So, and if you go to some landfills, you see this one, especially if you go into the night, go in the night, it's so obvious to see this huge light, the smoke, fire that comes out from these things. So the energy recovery is useful. As I mentioned, landfill gas is a good energy source. It's considered 500 BTU per cubic feet of energy versus 1,000 BTU per cubic feet of pipeline gas. So preferred for large landfills where you have a lot of gas, and putting the gas to energy projects are feasible. So once you extract that landfill gas, and then you can recover the energy using gas turbines, or IC engines, or you can use it directly as the boiler fuel, or you can upgrade the gas quality and then inject into the existing pipeline, and that can go into the common utility distribution system. So these are options that are considered. So obviously this energy recovery is good thing to do it, because alternate energy, anything that can substitute the fossil fuels is great thing to do from climate change point of view. But a lot of times it's the financial viability that it makes landfill owners to do it or not do it. So a lot of landfills that I visited, they used to do it when economics worked out. Now they shut down the plants because it costs more to produce this energy compared to the buying the energy. So there should be some financial benefit model to make these energy recovery options available. But these are the things that we. So one thing, so a lot of things are managed properly. So but there is an issue of this fugitive emissions. So as I mentioned, let's say even if you have, I'm showing here, let's say you have an active extraction well, so you're trying to suck up the gases, right? And then these extraction wells, you put at a certain radius, right? Certain spacing. And then depending upon the vacuum that you apply, and then there will be a radius of influence, right? So all the gas that is generated in the radius of influence could get sucked up, and then it gets collected. What about the areas that are beyond this radius of influence, right? So they tend to try to come to the surface, and even though you have a final cover, they might they will slowly find a way to come out. So these are the fugitive emissions, and these are substantial at landfills. And you cannot put these extraction wells at very small spacing to make this one go away. But even the extraction wells, as I mentioned, they are considered 60% efficient. So you have a 40% of the gases they're trying to escape. So this has been a major problem in the U.S. So we are trying to address this one. For example, if you have a dump site, then everything is emissions going into the atmosphere. So I'm talking about here engineered landfills that we have in the US. They are very well engineered. They have a very good cover, and we have extraction wells, but still, we have these fugitive emissions. So we're, if you have open dumps, everything is going to the atmosphere. That's really bad. So the idea is how do you address those fugitive emissions in a passive manner, right? Because they will come out slowly, and what do you do with this one? So what we are doing is, in our research, just giving you a flavor to one of our ongoing projects, is to think about a cover system a little bit different than conventional cover system. So what we are looking at here is a cover system. So let's say you have a waste that is generating the methane, carbon dioxide, and H2S. And then that comes to this layer that is a soil layer. Typically, we just have a soil layer. You have some methanotrophs in this, microbes in there. They convert, methane into CO2, but the amount of that conversion is very low. So, but if you add biochar to that soil, you're going to create nice conditions for methanotrophs to grow and multiply, and then you can get substantial oxidation of the methane into carbon dioxide. So this we studied, for many years, and we established that one. And recently, we try to look at, okay, hey, we're converting methane into CO2. The CO2 is getting admitted to the atmosphere, and the CO2 that is, coming in the landfill gas, That's untreated, and that's also going into the atmosphere. So can we sequester that CO2? And H2S also is a big problem. So can we, sequester the H2S? So we found out this slag layer can really, do that one. It can sequester the H2S. It can sequester the CO2. So, and then basically, methane is converted into CO2, and CO2 gets sequestered here, H2S gets sequestered here. So these are the main components. We haven't looked at, what happens to that NMOCs, but they could also be addressed in some way in this kind of a biogeochemical cover system. So practically, we have zero emissions. So we are trying to say that we are developing this zero emission cover system for landfills. So I have a small video. That's the last thing that I have to show you. That tells you this only 2.4 minutes video, and it explains to you this project that we are working on, this research project. Can you hear the sound?
No, sir.
You cannot hear the sound?
No.
Okay, just 1 second. I just need just. That's what I want. Okay. I want to share the screen again. And I think this one, share sound, and this one. Okay, now it should show. So this is a small video that you can see. Can you see? Can you hear now?
Yes, sir.
Greenhouse gases are a major cause of global climate change, and municipal solid waste landfills are a major human source of these emissions. Landfills are a major source of methane, carbon dioxide, hydrogen sulfide, and other non-methane gases. Most modern landfills are engineered with gas collection systems.
Can you see this
to
one,
capture these
Hanuman?
gases. However, these systems are not always 100% efficient
Yes, sir.
due to the limited radius of influence of each gas collection well. As a result, the gases escape, making fugitive landfill emissions a major environmental problem. Exacerbating the problem, in many developing countries, landfills do not have gas collection systems. So greenhouse gases are directly emitted into the atmosphere, significantly contributing to global climate change problems. In order to mitigate these fugitive landfill emissions, we are developing a biogeochemical cover system, which consists of biochar amended soil and steel slag. Our results show that biochar amended soil has significant potential to mitigate methane by oxidation, and steel slag has the potential to mitigate carbon dioxide and hydrogen sulfide emissions through various carbonation and sulfidation reactions. Here's how it works. Landfill soils have methane oxidizing bacteria. However, the bacterial activity needs to be enhanced for effective methane oxidation in the soil. Biochar amendment provides a favorable environment for the bacteria to colonize. It has high internal porosity and high specific surface area, which provides greater moisture retention and greater surface area for the microbes to colonize. As a result, biochar amended soil leads to greater methane oxidation. Steel slag is produced as a byproduct during steel manufacturing process. The slag is rich in alkaline metal oxides and iron oxides. Calcium oxide can bind carbon dioxide in the presence of moisture and form calcium carbonate. Similarly, iron oxide can bind hydrogen sulfide in the form of iron sulfide. Through these chemical reactions, the slag sequesters both carbon dioxide and hydrogen sulfide. We developed findings through small batch tests, small column tests, and near field scale column experiments in our laboratory. Then, we performed field test plots to affirm the findings in the real field setting. Our results confirm that by bringing together biochar amended soil and steel slag in a biogeochemical cover system, we can mitigate the fugitive emissions of a landfill. For more information, visit us online.
So hopefully that the brief video has given you the information about the project that we are working on. And we published several papers on this one, so you can find more technical details on this biogeochemical cover system. And it's based on the waste materials and very inexpensive, and it could be put on the dump sites too. So it's an ideal type of the cover system that can go in. And by the way, I think my PhD student Jyoti Chetri is, I think, joined. She's working really hard on this project. So just in closing, I think I'm out of time. So just want to mention that the landfill design, construction, operation, closure, and monitoring methods are well established in the US. And based on the monitoring data for over 30 years, engineered landfills are shown to be protective of public health and the environment. Research is in progress to make the landfills even more effective and sustainable. So that's what we are trying to do, is trying to work on bioreactor landfills, biocovers, and innovative end users to make the existing landfills to be more sustainable. I recommend everyone to review thoroughly what others have done through literature search and then develop inexpensive, efficient, indigenous systems. So, just because it's done in the US, you don't have to do it in your country. So you really always have to look at the local conditions and develop the local solutions. So again, I want to end with this textbook. So landfills and impoundments. I really want you to have hands-on this book. So you have a course material to teach a course such as landfill design course. So with that one, this is my contact information. Feel free to contact me anytime through email, or you can go to this my websites. You can find the publications and other details on our research. Thank you very much, and I want to. I just took all of my time. Probably, not sure if there is any time for questions or not. So I will turn it back to the organizers. I'm going to look at the chat box and look at any questions that you have. I'm going to respond while the next talk is going on. And also, I will put a copy of my presentation in the chat box when the other presentation is going on, okay? Thank you so much.
Thank you so much, sir. So thank you so much for sharing this excellent research work. I hope so. These kind of research work is very new to most of the participants. So try to understand and grab the knowledge, whatever has been done. So most of the research work, it seems it was done very recently based on all these publications. So I think you can able to download most of these publications also. If you are unable to download, you can also approach, or you can also directly write to Prof Reddy. So you'll be happy to share all these results. Okay, and do not see only these results in terms of the laboratory viewpoint. Most of them have some kind of a practical relevance. And if you see these in terms of the laboratory, then try to validate them with the field studies. So that is the best way of learning, augmenting the research. So we have only 2 to 3 minutes time. We can take quickly 1 or 2 questions. So participants, please unmute yourself and pose 1 or 2 questions quickly. Anybody? So please unmute yourself and you can ask your question.
Hello, sir.
Yes.
Yes.
Sir, actually, I don't have any questions, sir. Regarding your book in environmental engineering, I want to ask one thing, sir. Actually, sir, the book is, whatever the price of the book in US, it is the same price in the India also, sir. So can we have a Indian version of the book, sir? Otherwise, what happens, whatever the interested students, they have to take the book only from the library, sir. They cannot have a personal copy, sir.
I know that's that's the problem that everybody's facing. You know, my idea of writing the book is to make it accessible to the students. But the book was written in 2004, and it's published by John Wiley. During that time, the ebook, concept was not there. It was not that long ago, but still, that ebook concept was not there at that time. So I've been asking the publisher to create the electronic version of it. That's one thing. And other thing that I'm asking the publisher is to create an international version or like a cheap edition for developing countries. Um, so I will keep trying. I've been not successful with the publisher. So that is a major challenge. So what I see is the libraries are getting one copy and the students are basically having access to that. Even the instructors are having access only to the library copy. So that I really feel really bad about this situation, because the whole idea of writing the book is to make it accessible to the students. So as you know, as an author, you don't get anything writing a book, but publishers make all the profits. And I've been pushing, so I will try to follow up again and again. So let's see if they take it seriously.
Thank you, sir.
Yeah, so thank you all.
Yeah, thank you very much, Rao, and thanks everyone for your patient listening. Thank you.
Thank you, sir.